This is my project for EEC 483, Computer Organization, Spring 2020 semester. Project 3, Building a Cache Simulator. So I'm going to just start with running through the code here, just kind of scrolling through it. And I'm actually going to build it right now. Let it compile. Awesome, succeeded. Very good. So to start with going over through the code, I started with including some of the typical C libraries that we were going to be using in this. And I also defined some variables such as the address bit, the read and write, and instruction fetch, which as mentioned in your instructions, the read is 0, write 1, instruction fetch is 2. So we defined some variables unassigned integer, 32 bits. Then we have our method to set the block size by shifting the bits. So we basically shift the bits and then we set that variable, that bit to 1, meaning we get our block size, which is 16, 32, 64, or 128. And then we have the method to get our tag number here. And then we have our cache simulator method, which is pretty lengthy. Scrolling through it. Here. So to start with the cache simulator, basically what our cache simulator is going to do is it's going to read a memory trace and simulate the actions of the cache. So the simulator keeps track of which memory blocks are loaded into cache. As it processes each memory reference from the trace, it checks to see if the corresponding memory address is in the cache or not. So we start by first making our cache block table set to null, meaning that there's nothing in there that's 0, and then declarations of our variables. So some of these variables that we're going to use for our statistics and cache parameters that you will see in the output. So then we calculate the offset bits here, and then we calculate the index bits here. We calculate the tag bits right here, and then basically make our cache table to store the data. So essentially it reads the file and it does a total count of how many total items there are in the file, and essentially the type of input it is. So whether it's a read, write, or instruction fetch, which as mentioned earlier was defined as 0, 1, and 2, 0 for read, 1 for write, and 2 for instruction fetch. If, however, for some reason the access type is unknown, it'll print unknown access type and exit the program, which in our case we did not have happen, which is a good sign. And then we search our cache table. So we check the whole set in our cache table, and then what we do is if we have a cache miss, we load the block into an empty block and timestamp it. So the reason for the timestamp is so using the LRU method, we are able to replace the one that's been unused for the longest. So moving forward for block replacement, we basically essentially just check whichever one has been unused the longest, and then we replace that block. And then here we have pretty much just print all the results, all the statistics and parameters as mentioned is basically the objective of the project. And then we do like a memory cleanup, memory dump, so essentially when we run it back, nothing messes up or anything like that since we were using cache memory. Here we have our main program, and basically what our main program does is it essentially takes a trace file as an input, which takes a pretty much a text document as an input. The 4 files that we have here are the ones that were provided for this project from your website, and also that were found in the instructions as well. So we declare some of the block sizes, which is 16, 32, 64, 128, which we use these block sizes to pass it in as one of the parameters so we can kind of know what is the size of our program that we're doing. And the set types, so depending if we want, direct mapped cache or 4 set associative cache or 8 set associative cache, which is another parameter that gets passed in into the cache simulator method. And then our cache size is 64 times 1024, which is 64 KB cache size. And we make a file pointer. So basically what this does is it takes an input as it reads a file input. And basically if it reads the file, that's good news. 0 to 4, 0 to 3 array indexes is filled. and it prints the name of the file. If it can't do it, then it prints that it can't open. It prints that it doesn't open. It can't open the file. Here it prints that like the name of the file. If the file is found, file I, depending on which file it is, it'll print the name of the file. And then we have our basically we print the associative cache that we're on, depending on which one we're running, and then we call the cache simulate cache method, which basically runs the simulate cache method that we recently went over. It makes a cache table and it outputs the results. Then we close it and we are done. So now I'll build the project again, even though I did it at the beginning of the video, let it compile up to date, and then I will let it run on the console here a few times. So we see here it's printing all the different statistics for the different set associatives and the different memory reference traces. So in total we get 48 results. It's printing statistics such as the number of accesses, memory read events, memory write events, the instruction fetch counts, block placements, block replacements, the total number of blocks, the number of hits, misses, and of course the ratio of the hit and miss ratio altogether. I will stop it now because it's going to take a while for it to print all 48 results, but it will be included in the submission file of the video.